Hi everybody, this is Mr. Folly, and I have to admit, Mr. Folly made a boo-boo, and what he did was he messed up a computer, so he is now stuck with a worse one. So, because I messed up my other one. So, I'm trying a different format so I don't go as crazy with it, so we'll see how it works. We're going to talk about electron configurations today. Excuse me, noble gas configurations. And I just want to point out no quantum number, so if that happens to trickle into anything, you are good with it. So we'll get through that. Okay, so electron configurations. So let's just suppose I can stop my. No, that's not what I want to do. So electron configuration. So what we're going to do is we're going to identify where electrons are. So we need our periodic table now. So get out that handy dandy little thing I told you had to print called the periodic table. So I'll take a deep breath now. Okay, go get it. Come on, you can get it. You can get it now. It's all right. It's all right. It's all right. It's all right. Okay. So maybe remember this. We had 1s2, 2s2, 2p6, and that's all you remember. There's numbers, there's superscripts and stuff like that. The first number right here is the row. So if I were to chop my periodic table into pieces, I would see that the first row has only hydrogen and helium in it. My next row, row 2, so this would be row 1. Row 2 would start with lithium and go across. Okay. The letter is the block. As I'm looking at this, and I held my old stuff, I can't believe I didn't write this out a little better. So this is the S block. Okay. So on your periodic table, you want to draw a little ghetto periodic table. I suppose I'll color mine in. There's my S. The next block is the one all the way over here called P. And this guy right here is P block. And these letters stand for something that we don't ever remember. I don't remember what they are. I looked them up once and it's completely forgettable. There's a SP. And then the next one is D. Okay. And I'm going to call D. No, I didn't write D in there. I meant to. I'm going to call that D minus. And then the last block is the F minus minus. Okay. And the reason why I'm going to do that, D minus just seems to flow with such great beauty and pride. I hope you haven't experienced the D minus or the F minus minus. I will tell you now, I have given an F minus in class before. It used to be if you got less than 55% in my class when I taught, and we'd fill out the little bubbles, I gave people F minuses. I had a parent get mad at me because their kid got an F minus. Okay, so what this is basically is a counting game. Okay, so now we know the letter is the block. Check the row. I can count that. Check the superscript. These are the superscripts. That tells you what column. So in the S block, this would end in 1. Everything in here would end in 1. Everything in here would end in 2. Okay. If I'm in the D block, it'd be 1, 2, all the way up to 10. Okay. P block would be 1, 2, all the way up to 6. And the F block would be 1, 2, all the way up to 14. Okay. All right. So the superscript tells the column. So now you kind of have that. When is the number not the row? So the D block and the F block. So if you're the D block, you're D minus. That means if you get all D's, it used to be 100 years ago, if you got all D's, they would flunk you and hold you back a grade. Okay? And if you got F's, they would hold you back 2 grades. Not only would they hold you back, they would kick you back to the earlier grade. So if you flunked 4th grade, you would have to take 3rd grade over again and then 4th grade over again. They decided that all this did was make delinquents. And then you had like 20-year-old 6th graders trying to find a date for prom, which is really creepy. So what this means is if I look at scandium, scandium is number 21. Okay, so scandium is number 21. And do you see that scandium's in the D block? It's right here. Okay. Now you would think scandium then would end in 1, 2, 3, 4. It's in that 4th row. So scandium you'd think would be 4D. It's not. It's D minus. So that means it's going to be 3D. It would end in 3D1. Okay, so that's where the D's are minus, meaning you'd think it would be 4, but minus 1 would make it 3. Okay, and F is minus minus, and we'll get to those in a minute. So let's do some examples. Fluorine. Okay, so if you look in the periodic table, and I'll draw my little ghetto periodic table. Um, 1, 2, 3, 4, 5. Oops. 1, 2, 3, 4. Good. And F is right here. Okay. So when I do this, I'm going to start off in the top. Okay. So the first electron I'm going to look at is right here. Okay. So it's going to be 1 S. When I fill this in, there's 2 of them. S1, S2. Okay. And I come down to the next row. It's on the second row. Right. So I'm looking at lithium and beryllium. Okay. They're both in the S block. And there's 2 of them. So it looks like squared. Okay. The next time I jump over here, there's going to be boron, right? Carbon, nitrogen, oxygen, fluorine. Okay. So if I have that right there, then I'm still on the second row. I'm now in the P block, and I have 1, 2, 3, 4, 5, 2. Okay. And that's it. I now have the electron configuration. Okay. Now in reality, the ones we care about the most are the outer ones, and these are the outer ones because they have a capital 2. That's the second energy level. Those are called valence electrons. Oops. Valence electrons. I'm going to rewrite it. Okay. So I want to do selenium. Selenium is number 34. Selenium is going to end up in the P block, just so you know. So I'm going to start right off. So I'm going to number these guys. So it's going to look exactly the same at the beginning. The first 2 electrons are 1s2, hydrogen and helium. So you should have your periodic table out right now. The second column, lithium and beryllium, are second row, S block 2. And then the next part is going to be, these are numbers 3 to 4. And then numbers 5 through 10 are going to be second row, P block 6. Okay. And then that gets us to 10. Then I'm going to look at numbers 11 through 12. See how the block ends there? And that's going to be 3S2. And then 13 through 18, still in the third row, P block 6. Okay. So far, so good. All right. Now I'm going to shrink this down a little bit. I hope. Oh, it's not going to work. Okay. I'm going to shrink this down a little bit. Oh, I got everything but my 6, but that's okay. Shrink that down a little bit because I need a little more room. Now from 18, I have 19 to 20. Numbers 19 to 20, 4S2. And then my next block is going to go 21 to 30. 21 to 30 is the D block. I'm still in the 4th level, but it's a 3D. Remember how you'd expect it to be 4, but it loses 1? 3D 10. That gets me to 30. And then to get to selenium, I'm back in that P, so 31 to 34, I'm back on that 4th level. Okay, so notice, that's good. The only time you fail is in the D block. You hop back to the right one. 4P, and then selenium would be gallium is 1, germanium is 2, arsenic is 3, selenium is 4, 4P4. Okay. I'm going to highlight what you have to show. Whee! And that bottom part you don't need at all. I was just hoping it would help you. Okay. I'm just going to do vanadium and not calcium. How's that sound? That sounds good. All right, so I'm going to ignore this one because I want to get you out of here. So it's almost exactly the same thing. Vanadium has 23 electrons. So what I'm going to do is I'm going to go all the way up until I have 20 electrons. You have 20 electrons here. And I'm going to copy it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So this gets me to 20. See how I just copied this right here? So anything that has more than 20 electrons will start exactly the same. Okay. Now I have 3 electrons left. So that means I have to do 21 through 23. And I'm on that D block again. So I'm not going to be 4D anymore. Minus 1, 3D, 1, 2, 3. PT. Orbital notation. Okay. Boxes are orbitals. Now, that's not an official thing. That's a useful thing. Orbitals hold at most 2 electrons. So if I have, I have L box O. An electron is an arrow. It would be up and down. It holds at most 2. So that means it could be a box with an up arrow. Atoms are lowest energy when a block is full. Okay. Atoms are pretty stable when a block is half full. Okay. So believe it or not, these things come in batches. So like that. So these would be the p orbitals. Okay. So it says a block instead of an orbital. So their lowest energy when a block, all of the p orbitals are full. And it's pretty good when it's half full, and the rest of it is junk. Okay. So right now, junk. Hey, that's kind of stable. Okay. Junk. Hey, that's really stable. Okay. So when I said it's stable or it's not, it's based on that stuff. Okay. It won't erase for me. It's not erasing. There we go. So now did you notice on orbital notations, we get to see this part right here is called Hund's rule. Everybody in the same block gets 1 before. Whoa, I lost my page. Before an orbital gets 2. Remember, an orbital for our purposes is a box. Really what an orbital is a region of space where an electron exists. Okay. Well, what is a box? A region of space where something exists. Whoa, that's deep. Okay. Bogey. Examples. So we're going to do some orbital notations here. So what I'm going to do first is show you the way it'll be set up if it's multiple choice. 1s has 2 electrons, right? So if has 2, I need 1 box. And then 2s2, that would be 1 box. And then if I have 2p6, see how p6, there's 6 electrons, 3 boxes. Okay. So nitrogen, I'm going to write the electron configuration of nitrogen. It's 1s2, 2s2, 2p3. Okay, that's right. So 1s2, put 2 electrons in that box. 2s gets 1 box. It's 2. 2p, now 2p has 3 boxes. And I have 3 electrons. I have to give each one at a time. Okay. So if you look at it, you've got to get used to 1s, 2s, 2p, and then the next one would be 3s, which would just be 1 box, and 3p, which would have 3 boxes. Every once in a while, AP Chemistry will show it slightly differently, of course. So I'll show you that method now. Okay, so here's magnesium. I'm going to write magnesium's electron configuration. 1s dose, 2s dose, 2p, 6, yeah, my Spanish isn't very good, 3s dose. So now I'm going to do the other way you see it. 1s, 2s, 2p, 3s. I'm going to erase that straggly line. 3p, 4s, and we'll see where it goes. Okay. So if we have all these things right here, I'm going to start with 1s. It says there's 2. It's the same thing, but the box doesn't have the container. 2s. Now, let's think again. Why does this have 3 boxes? Well, if it has 6, remember a box can hold at most 2 electrons. So in order to hold 6, it's got to have 3 boxes. And you must fill them in the order of up, 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 down, down, down. That's just the way they go in. Okay? 3s only has 1. 3p again would be, oh, wait, it gave us all these things, and this is just empty. Oh, looky, looky, looky. Those are all empty, and I'm done. And that's it. Okay? So that's an orbital diagram. Okay? So it is important to know, and make sure you write this down. I'm going to even change my pen so you can tell how important it is. This is the lowest. Oh, man. That didn't work the way I wanted to. Watch how I do this. This is my favorite way of doing this. This is the lowest energy. And as you go this way, this is the highest. So the highest energy electron in this would be 3s. Make it orange so you can see it better. Is it 3s2? Those are your highest energy electrons. Okay? So I'm going to get my highlighter off of being highlighting in black, which is creepy. And now we will go to why are noble gases unreactive. Okay. So orbital diagram of argon. I'm going to write the electron configure of argon first. 1s2, 2s2, 2p6, 3s2, 3p6. Okay. Orbital diagram, 1s, 2s, 2p has 3 boxes, 3s is 1, 3p has 3 boxes. Okay, so I'm going to fill this in. I got 2, I got 2, I got 6, up, 2, 3, 4, 5, 6, 2, 1, 2, 3, 4, 5, 6, and look at that. Okay, so the orbital diagram of argon is full. So why are noble gases unreactive? Because they are full. How about that? That's it. They're unreactive because they're full. Noble gas notation. Okay, so noble gas notation. Remember how I said way back up here that I said every one of them's the same stinking thing. You keep writing 1s2, 2s2. Look how they're the same. Look how they're the same. 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 So what the chemistry world has done is they've found a way to shortcut this. So the noble gases are the atoms on the right-hand side of the periodic table. They are helium, neon. I put H2 instead of helium, neon. Maybe I'll write one legibly. Argon, all the way down to radon. Okay. So those guys are full. And remember I said we really care about the outermost ones? So for a noble gas notation, what you do is you write the noble gas in brackets. Then start electron config again. Okay, so I'm going to look at bromine. Bromine is number 35. Okay, the preceding noble gas for bromine is number 18, argon. So I'm going to write argon right here and just make a note that he's 18. If argon is 18, that means I need to deal with 19 to 20. So bromine's at number 35. I got to get all the way to 35. But I'm just going to write argon instead of the first 18. So for elements number 19 to 20, I'm going to write 4s2. And for numbers 21 to 30, I'm going to write 3d10. And from 31 to 35, I'm going to write 4p. Uh-oh. Bromine doesn't go all the way to the end. It doesn't go all the way to 6. It goes to the 5th one. And this right here is my answer for the noble gas or core notation. The noble gas notation is also called AKA, also known as core. Okay. Now I'm going to skip silver because silver has been banned from the periodic table. I am, however, going to do promethium. Ooh, promethium, number 61, number 61. The preceding noble gas for promethium, number 61, is number 54, xenon. So I'm going to start with xenon. Beep, beep, beep. And then after xenon comes 55 and 56. I'm going to count on my periodic table. 1, 2, 3, 4, 5, 6. This is the 6th row, right? 6th row. S2. And that takes care of 55 and 56. 55 and 56. Now, number 57 is kind of all by itself. So look at 57, and then see how 58 is in a weird place. 57 is in, it would be 60. Remember, we got to do the drop down kind of deal. 5D1. Okay. Now 58 through 61, because promethium's number 61, is in the F block. Now, remember we started at 6, but F is a double flunk, right? So that means I'm going to be at the 4th level. Remember, it's F minus F. And then I've got 58, 59, 60, 61, and you missed me counting with my fingers to do that. That's it. There's your noble gas notation. All right. Valence electrons are lost during ion formation. S and P only are valence. If you're in the D block, you lose your S first. Then D only if necessary. So if I look at calcium on the periodic table. Calcium is right about here. This is the S1 column. This is the S2 column. Calcium ends in 4s2. 1, 2, 3, 4. Calcium ends in 4s2. Has 2 valence electrons. Chromium is argon. Bracket me. And then 4s2. 3D4. Now, there's something, I'm kind of feel bad I'm using chromium here. I'm going to change chromium to manganese just because this isn't quite the right way that it goes. And I used it. There was an old thing we had to teach. We don't have to teach anymore. So chromium is not a fair question. So I'm going to do manganese. Manganese has 1 valence electron. Okay, now this is not true. Manganese has 2 valence electrons. SB. Man, where's SB? SB's number 51. Woo, double doggies. Let's take a look at that one. So it's going to start out with krypton, which is number 36, 37 and 38. 1, 2, 3, 4, 5. 5s2, 4d10. And I'm looking at what? SB. And then it's going to end in P3, 5p3. Now notice it's only the S and the P's. I have 2 S. I have 3 P. I have 5 valence electrons. That's it. That's it. That's it. Review. Electron configurations are long. Noble gas configurations are short. Orbital diagram boxes hold 2. SP, DF have how many orbitals? Uh-oh. It's got dose orbitals, trace orbitals, Cinco orbitals, 7O orbitals. And then quantum numbers are gone. Sorry. But that's it. So we are fully finished here. I would say.